What's up, guys? So I promised I'd do a quick video rundown of this assignment, just to kind of succinctly put things together. So here we are, here we go. First page is, and it looks a little messy right now, but first page is just graphing this, and I graphed it in Desmos, graphed this data, and then I exported a picture. I can show you how to do that really quickly. In Desmos, we'll actually go to that that graph, or one of them. Yeah, sure, this one. When you create the graph in Desmos, you're going to go up here to this top corner where it says share graph, and export image. When you do that, it'll download an image for you. So you'll hit download, it'll download that image. I'm not going to do that, I've already done that. But after you download the image, in Cami you can upload it by, you know what, I don't even have that on here. Let's go to Cami and let's see what that looks like. And here we go. When you are here, there's a add media button, and you can add media. Go to my computer or whatever your image is, and you can put it in. Click on it there. So add media, you can add the media there and go add your picture and like blow it up like this. And then I annotated over top of it. So I drew these blue lines in for the first couple of problems. Answers to the questions: what is the significance of the slope? We already know that's the velocity. We looked at the graph from the Desmos graph that I created. We looked at the slope for that. That's this one here, where we saw the slope changing, and the slope was, if we start and go from 0 to and forward, the slope is increasing. It starts at 0, it goes up at 1, it's at 10, 2, it's at 20, 3, it's at 30. Here's the slope, by the way, if you're looking where I'm getting those numbers from. As I move along the graph, this is basically my x value. As I move along the graph, it goes to 40, 50, and so on. So the slope is increasing. All right, so the slope's increasing. So therefore, question 4, the velocity of the wheel is constantly increasing. So the slope's the velocity, the slope is increasing, therefore the velocity is increasing. When I connect the dots or draw those lines, those blue lines that are on this graph, 0 to 6 was the first one. I calculate the slope of that line. It ends up being 30 centimeters, and that represents the average velocity between 0 and 6. I do that for the other interval too, for question number 7 and 8. I draw the second line. That's this one here, this little one. And you can already tell that those lines are parallel. In addition to that, the slope of that line ends up being 30 as well when you calculate it. There's the calculation. And that represents the average velocity between 2 and 4 seconds. On the position time graph, I draw a tangent line, which I kind of sketched here, and I told you that you could do that by sketching the tangent line, which is a line that touches only one point on the curve, right here at 3. And I do that, and I could find the slope of that line by hand by putting 2 little points here, but that is the same as what I've got going on over here on Desmos, and I want to go to the point 3. So at 3, the slope of this black line is the tangent line. That slope is 30. This calculates it for me. When you guys are at home doing this, you would do it by hand, by plotting those 2 points and then drawing the line and then having 2 points far away from each other to calculate the slope. But that one ends up being 30 centimeters per second for the slope. The velocity at 3 seconds, or the instantaneous velocity, that's what that means. All right, so we're talking about the first 2 lines we drew were an interval, and then we're looking at the velocity at that specific point. So the velocity at 3 seconds, or what we call the instantaneous velocity, or velocity at an instant. The slopes we calculated end up being all the same. They're all 30 centimeters. 1, 2, 3. That means for constant acceleration, the average velocity of an interval is equal to the instantaneous velocity at the midpoint. So these are the 2 average velocities of this interval: 0 to 6, midpoint 3, 2 to 4, midpoint 3. All right, the interval is the same as at that point. And this question's kind of a little overkill a little bit. Consider if an object accelerates uniformly, calculating the average speed. Would the object ever be traveling that average speed? Well, of course. All right. If you look back at that Desmos graph, at the end of travel at 6, it's traveling 60 centimeters a second. Right here. All right. And at the beginning, it was 0. So from 0 to 60, you don't go 0 to 60 without passing through, at some point, passing through 30. And it turns out you pass through 30, if you're accelerating uniformly, exactly at the midpoint, right? If you're at 60 at 6 seconds and 0 at 0 seconds, halfway right in between, you would be halfway there. All right, that's kind of the pattern we get with average acceleration, or constant acceleration, excuse me. So yes, it is exactly at the midpoint. This next group was using the same data, but what we're going to be doing here is we are wanting to graph the velocity versus time graph. So using that same concept of the midpoint, time, being the velocity at the instant, all right, we're going to look at that. So we're going to find the velocity over an interval, or over these intervals, 0 to 1, 1 to 2, 2 to 3, 3 to 4, and so on. And we got to kind of fill this table out to help us out with that. So we find the change in time. That's the difference between these two. So 0 to 1, that's 1 second. 1 to 2, that's 1 second. 2 to 3, that's 1 second, and so on down that column. The change in position for those intervals. 0 to 5 is 5. 5 to 20 is 15. 20 to 45 is 25. 45 to 80 is 35, and so on. So we get the change in position and change in time, which is going to give us the velocity. This is exactly what we're doing. We're calculating basically the slope, all right, because our variables are position and time. So we're calculating the slope between these two intervals and finding what that is. So velocity is 5 over 1, 5. 15 over 1, 15. All right, using this equation here to find the velocity. And what we notice is that velocity is valid in the instantaneous velocity at the midpoint. So midpoint times 0 to 1, 0.5, 1 to 2, 1.5, 2 to 3, 2.5. So the midpoint time is our instantaneous velocity, is the velocities in this table. And as you fill out the rest of the table, you can go ahead and graph that graph in Desmos and insert the picture here, which is what I did. After we insert that picture, we get a line here, and our data falls on a line, so we want to find the equation of that line. If I find the equation of that line, I want to know the slope. The slope ends up being, this is velocity time graph, the slope ends up being it's increasing by 10 every second. So 10 centimeters per second every second. Notice I got centimeters per second per second. That's this unit, centimeters per second per that unit, seconds. And I end up with an equation that looks like this. Here's my y variable, v, velocity, equals the slope, 10 centimeters per second, and my x variable, time. I don't have a y-intercept because the y-intercept is 0, so I kind of put that on there. I do have a y-intercept, it is 0, and I'm not just going to write 0. We leave that off usually. But it does represent a starting velocity, so when I generalize the equation, all right, I end up with the slope is the change in velocity. Change in velocity is what we call acceleration, and that's what we've got here. We got the velocity equals the acceleration times time plus the initial velocity. This next one's going to kind of what we call linearize that initial graph. That initial graph was a curve and was a little hard to come up with an equation. We'd have to do some analysis with quadratic functions and all of that. And to make it simpler, we're going to graph time x versus time squared. So this table, all we're doing is squaring the time values in the first column. After we do that, we graph it. I put the graph in here, drew the line, and we're going to come up with the equation. The slope is 5. If you look at the slope of this line, you can find that pretty easily to be 5 centimeters per second squared, and then the time squared. So I've got that same linear equation. Y variable is position, slope is 5, x variable is time squared. And that gives me an equation here too. Couple of questions to follow up with that. They're asking you what's the significance of the slope of a velocity time graph. That's the change in velocity over the change in time, which is acceleration. If I'm changing velocity, I'm either speeding up or slowing down. That's what we define as acceleration. Compare the slopes. Well, the slope of the velocity time graph was 10, and the slope of the position time graph was 5. They are exactly half of one another, or one's half of the other, excuse me. But that means it's half the acceleration. Since I know the slope of the velocity time is acceleration, the position time graph is half of that number. That must mean it's half the acceleration. Does that make sense? Hopefully it does. Here, we've got the acceleration there, and this one ends up being half of that. So it's half the acceleration. So I come up with an equation. We already kind of did this one up above for that graph. And for the other graph, I come up with this equation. Position equals 1/2 acceleration times time squared. Question 19, you guys should already know. That's kind of a review. We know the area under the curve of the graph of velocity time is the displacement. That is all. Hopefully, if you guys have questions, let me know. You can stop, pause, rewind, go back, whatever you need to for this video, and hear that explanation again. Thanks.